industrial paradigm again. What I discovered was that in just recent years, that there are other uses for biochar that are as good as anything in agriculture. That it is a binder in cements or in bitumen and highways. It's a replacement for sand in some of these composites.
Right.
And when you start to talk about that, it opens up a new world of what you can use for a source. You can use municipal landfills and get the carbon parts out of that. You can use biosolids from waste treatment facilities. All of these wastes that are now causing problems for us can become resources. We can close those loops by putting them into hardscapes like buildings. And when you do, you have other benefits. They self-heal, the buildings self-mend. They produce regulated humidity in the indoors. So even though it's quite hot outside, if you come inside and the humidity is at 50%, you feel better even though it's hot. And you have the removal of mold spores and pollen and dust and toxins. So it's biobiology. You're able to clean sick buildings using these substances as paints or plasters. And now you've got the possibility of making some of those polymers with the carbon that's coming from these processes. And you can make 3D printing feedstocks. You can make batteries, fuel cells. They're excellent cathodes. They have these cation exchange capacities that make them superior in many ways. And so now you're starting to think about the carbon cycle in a different way. We've been portraying it as this evil, as this enemy, something that has to deal with, that's just like a menace to us, the carbon dioxide. And actually, it could be our biggest friend. Carbon is a miraculous molecule. It's formed in the rare occurrence of the death of a star when it reaches a particular point in its death, when it has a very short interval there where this particular physical-chemical reaction can occur that creates carbon. And then that wafts off into the winds of space and wanders until eventually it comes to rest on a planet such as ours. Miraculous.
I've looked at water as the carrier of consciousness. But I haven't looked at carbon, so that
they work together.
Yeah.
They're part and parcel. And carbon is the building block that water endows with life. And carbon is a unique bonding element because it can form these different states, just like water, right? So water has 3 or 4, maybe even 5 states, and you have a carbon that also has these different forms, anywhere from a rock powder to a diamond, and graphite and activated carbon and a wood vinegar that's carbon and things like that. So it has these different forms, and it's what happens when you put it into a furnace and you raise it to 400 to 700 degrees. It can be even hotter than that. It changes its molecular bonding and goes from a labile form, that's the kind that plants need to grow, and that goes back to the atmosphere as a gas, and then returns in the rain to make more plants.
Is that like a graphite bonding? Or?
Yeah, it's similar, but the labile form is a very open bond form, easily broken by microbes in the composting process.
Right.
And then when it gets to the graphite form, the activated carbon form, that form of recalcitrant carbon, the bonds become more like buckyballs. It bonds to itself. And when it does that, it's difficult for microbes. They would have to spend a lot of energy to break those bonds, and they don't want to do that. There's a conservation of energy, and so they have other choices in life than spending their time gnawing away at a piece of hard carbon. So they don't, and as a result of that, you can find biochar now. The geology of it is such that we now have found a 250 million year old biochar from forests from a time when Europe and the Americas and India were all joined into a single continent. At that time, they were the earliest forests, and there were forest fires, and those forest fires in the right conditions produced the temperatures for pyrolysis and burned off the gases and left behind the carbon. And so we find biochar that's that old. The typical excavations in Brazil or the South America for these early forms of farming 4,000, 8,000 years. There is a small degradation in the soil, mostly related to microbes that are very persistent, but very small. So it persists a very long time. And what happens then is now you're thinking, how do we get the carbon out of the atmosphere? And the way is to starve the atmosphere of photosynthetic carbon. So instead of going back as a gas, it's held in the soil. It becomes structure. It holds air and water, and microbes use it for a home, and it's just structure in the soil. And in that way, we prevent carbon that would otherwise go there from going there. And over a long enough time, that winnows out the carbon in the atmosphere. What's up there starts to rain down more than it's being replenished. Now we have wild cards like melting methane clathrates and melting permafrost and things like that are putting more carbon up there. Fracking is putting an amazing amount of methane up right now. Right. So we have all these bubbles still to go through, and these wild cards. We don't really know whether they'll survive. It's still a major challenge. But there is hope in the sense that as more people begin to farm and to use these carbon features in new and better ways, we can catch up. We're going to have to change how we live, though, because we're coming to a change in available energy, coming to a change in resources of all kinds, including water. And so humans we've reached the edge of the Petri plate.
Right.
And if we continue growing as if we had an unlimited supply of agar and more Petri plates, we're going to die because we will have reached the end. If instead we can realize that this is just another stage of evolution and we graduate from being children, juveniles, and juvenile humans, to a more mature, more complex species as part of a larger ecosystem and live within its limits, then we can survive.
I feel as if it's time to say, well, and thank you, Albert.